Before starting today's class, I will explain about the final design lab, the lab number 4. So I will post the lab number 4 on the Blackboard today after this class. So I will explain. So, sorry. In the previous lab, you were requested to implement single cycle processor. And then this single cycle processor supports additional branch instructions, including 7 instructions we learned in the textbook. So, and the goal of this final lab is to implement 5-stage pipeline processor. So in chapter 4, we learned about the pipeline process architecture. So these pipelines are composed of 5 stages: instruction fetch, instruction decoding, execution of memory. Write back. Oh, I can write. So also this 5-stage pipeline processor need to support the same instructions. So we implement on the design lab number 3. Okay, so you need this processor need to support these instructions. Okay, so BNE and BLT, BGE are sorry, included in the this supported instructions. Okay, so but I want to change the design of this pipeline processor. It is because actually the 5-stage pipeline processor introduced in the textbook has some significant not errors, some significant design drawbacks. So actually one student found this drawback. So that means, so actually in the pipeline, in the 5-stage pipeline, the processor of the textbook, in order to reduce the control hazard, the comparator is moved to the ID stage, and then this comparator just compares the equality of the 2 output from the register file. And then actually the one student found the some design errors. So the problem is that, so actually the branch instruction like BQ receives data from, can receive data from formal instructions like load X1. Okay, so in this example, this BQ received the result from the formal load instruction. That was the problem. So in the 5-stage pipeline processor, we implement the forwarding path in execution stage. Okay, so forwarding boxes are in the execution stages, and then the results are forwarded from the memory and write back stages. Okay, that's the problem. If the BQ, the branch instructions, is determined in the ID stage, then this BQ cannot receive the forwarded data from the memory or write back stages. Okay, so actually this BQ can only receive data from register file. So actually in the chapter 4, I explain the data hazard, so one kind of data hazard, and then so I explained about the only load use data hazard. But as the branch instructions are enhanced for reducing control hazard, the BQ also, we need to also consider the BQ for this data hazard. Okay, so that means if the next instruction is the BQ and then the former instruction is the any archive instructions or load instructions, then this BQ need to be stored in ID stage, okay? Because PQ can only receive operands from register file. So until this data the result is written back to the register file, the PQ needs to be stored in the ID stage. So that's the problem of the 5-stage pipeline process architecture introduced in the textbook, okay? So actually in the previous semester, I also I also made the students made the student design 5-stage pipeline processor. But in order to handle this issue, the hazard detection unit was so difficult. So it's so complex actually. So it's difficult to be implemented. So so it was difficult. Okay. So the project of this semester, for the project of this semester, I modified the branch instruction slightly. So that means the branch instructions, actually the branch instruction, this branch unit need to support the additional branch instructions like BNE, BLT, and BGE. So that means these branch instructions cannot be handled by comparator like BLT and BGE. So what's the problem? We need to compare the magnitude of two operands. Okay, so this BLT and BGE cannot be handled by this simple comparator. So we need to implement the subtractor. Okay. So instead of using ALU, so I slightly modified this structure of the execution unit. So the branch is handled by dedicated branch unit. So this is the branch unit. And then this branch unit received the output of the forwarding boxes. So as you can see, the output of the forwarding boxes are connected to the input of the ALU, and also the branch unit received the output of the forwarding boxes. So that means the branch unit is the behind of forwarding path. Okay. So that means the branch unit can receive the forwarded data from the former instructions. Okay. This is some. I think this design is better than the design of the textbook. Okay, the branch unit is behind of the forwarding path. Okay, and then these branch instructions like BQ, BNE, BLT, and BGE are handled by branch unit, and then this branch unit exists in the EX stage. This is the EX stage. So I modified this project. Okay, so branch unit exists in the EX stage, and then branch units handles additional branch instructions BQ, BNE, BLT, and BGE. And then the result of the branch instruction is determined in EX stage. And then the target of the branch instruction is applied when the branch instruction is in the memory stage. So it's also slightly changed from the design in the textbook. So if the branch is taken, then this result is immediately updated to the PIC next. And then in the next cycle, the target of the branch instruction is updated to the current PC, and then the instruction memory is read by this current PC. So when the branch instruction is in the memory stage. So this is also the modification. So In this final design lab, you will be requested to implement the 5-stage pipeline processor. So actually, so I also write some explanation on this design document. So please read thoroughly this document. So it will be very helpful. So in the chapter 4, I mentioned that actually the idea of pipelining is very simple, but the detail is very complex. So what are the details? So details are like the forwarding path, the hazard detection, and then exception handling. So those are the kind of details implementation. And then actually those details are very complex in the pipeline architecture. So please remember the idiom, the devil is in the detail. Okay, the details are very, it's a difficult part. Okay, so please read thoroughly the document, and then so you can find some additional explanation about the project, final project. So as I also introduced some design tips with system Verilog. So system Verilog supports the structure type. So this structure type is similar to the structure of C or C++. So we can group the multiple signals in this structure. Okay, so it is very convenient. And then we can easily implement pipeline registers with this structure. Okay. As I explained about the internal forwarding of the register file. And actually this internal forwarding is already implemented in the register file. Okay. Well, you need to implement the forwarding unit and then hazard detection unit also. Okay. And then like the previous design lab, I also provide the instructions, and then the instructions are loaded into the instruction memory, and then also I provide the initial value of initial data of data memory. Also I provide the initial data of register file. Okay, so you need to complete this. What's I forgot the name of the module. Okay. So you need to complete the pipeline under the CPU.sv, and then also I provide the test bench file like the design lab number 3. So actually you can only instantiate the top module on the test bench. Okay, and that's it. So you can simulate your top module with this test bench. So if you run this test bench, then test bench will generate the report file. Okay, like the design lab number 3. Also, for this lab number 4, I provide the golden version of the single cycle processor design. So this is the completed version. So even though you failed to complete this lab number 3, please try to implement the pipeline processor for lab number 4. Okay, because I provide the golden version of the single cycle processor design for this lab number 4. Okay. Any questions about this lab? Good. Okay. So I believe that this design lab will be very helpful for you to understand the detailed architecture of a pipeline processor. So actually many students struggle to understand how pipelines work and then how the data and control signals are organized in the pipeline architecture. But this is very critical, and this is very important for students to to understand the detailed architecture of the more simple process. Actually, it is simple, and then understanding pipeline architecture is also very critical. So I hope every student can understand the detailed behavior or detailed architecture of pipeline process. So as I mentioned, this is very simple. This is a very simple processor compared to our modern processors, but it's the very fundamental basic of the computer engineering or computer science study. Okay. So in the previous class, we learned about the basic of cache. So I also explained what are cache memories. So cache is the temporary storage space. Then why do we use cache? In order to improve the performance of computer systems. So actually, you need to remember that this memory hierarchy. So cache is located between register file and main memory. And then why do we use cache? Cache is fast. So that means if data is found in cache, then this data can be transferred to the processor very quickly. But main memory is very slow compared to the processor speed. So if the data is found only in the main memory, then the performance of this processor will be very slow. Okay. And then also I mentioned that cache is the small memory. Just cache is the small storage space that store the frequently used data temporarily. Okay. So you need to understand which data will be stored in the cache, and then how the data can be identified by processor. So which data will be stored? So which data will be stored? So I explained that we need to exploit locality of data observed in the application. So in order to exploit this locality, like spatial locality and temporal locality, then if a certain data is requested by a processor, then this requested processor is stored in the cache, and then neighbor data. So neighbor data are also stored in the cache. So this is so which data will be stored in the cache? So if for certain data is requested, then this data is stored in the cache. Why? In order to exploit temporal locality and spatial locality. And then how to identify data in the cache. So I explained that we can identify a certain data with address. So if we store, but the size of the cache is very small, so all data cannot be stored in this cache. Only the selected data is stored in the cache. Then we need to identify which data is stored in the cache. So in order to identify data, we use the address. Okay, so when the data is stored in the cache, this information, address information of this data is also stored in the cache. Why? We need to identify which data is stored in the cache. So just remember. So I explained that this is the architecture of the 5-stage pipeline processor. So so in the chapter 4, we learned that this is the instruction memory, and then this is the data memory. But actually, this is L1 instruction cache, and this is L1 data cache. Okay, so you need to remember that. Also, the previous class, we learned about the direct mapped cache. So cache is also a memory. So that means when the data is stored in the memory, so we need to also identify the location of the data. So that means that we need to decide which entries are used for storing data inside of the cache. Okay, so there are many different methods to decide the entries of stored data, allocated data inside of the cache, and then we will first learn about the direct mapped cache. So in the direct mapped cache, this is the cache block. So the data is stored in this cache block, but when the lower part of address is used as the index of the cache. Okay, this is the direct mapped cache, and so that means if a certain data has the same lower part of the address, then that means that these data are mapped to the same index of the cache. It's like 001, 001, 001. Okay, so that means the index number of cache is identical to the lower part of address. So this is the direct mapped cache. So if two data has the same lower part of addresses, that means that the index number of cache is the same, like this is A, and this is the B, and this is the address of the A is the 00000, and the address of the B is the 01000. And then let us assume that we use the lower 3 bits as the index of the cache. So, and then the first A is accessed by processor, and then B is requested by the processor, the same processor. So when the A is requested by a processor, this A is stored in the cache with the index of 000, index number of 00. And then the B is requested, but the address of B is 01000. So B has the same index number for this cache. So in this case, but the problem is that this cache is the index number 000 of this cache is already occupied by data A. And then we already know that the data B should be allocated to the same index of the cache. So how can you handle this? So A is evicted from this cache entry, and then B is allocated to this target entry of the cache. So A is removed. So this is called the eviction. So eviction means that it's kicked out from the cache. So A is evicted from the cache, and then B is allocated in this cache entry. Okay, that's how direct mapped cache works. So it depends on the size of the cache block actually. So I will also explain about the size of the cache block actually. That's a good question. Okay. So let us assume that this is the cache, and then this cache and 1, 2, 3, 4, 5, 6, 7, 8. So let us assume that this cache has 8 entries. And then the size of a single entry can vary. So I mean vary. What does that mean? The size of a single entry may be 4 byte or it can be 1 byte, or 2 byte or 4 byte. So it depends on the cache configuration. The one entry may store the multiple bytes of data, or one entry may store only 1 byte of data. So you need understand this. So what's the problem? So if we use the load word, then this load word requests the 4 byte of data. And then usually we use this 4 byte of data. Okay. But only 1 byte of data occupies this cache, then this data occupies the 4 different entries. And then it's inefficient actually. So usually the size of a single cache entry is larger than some data unit requested by load instructions. Okay, and then it's actually, Intel processor, the cache entry size is usually 64 byte. Okay, 64 byte. So what does that mean? So let us assume that this size of the single cache entry is the 64 byte, and then load word requests the data from the memory with the address of 0000. Okay, so you need to remember that the address handled by load instruction is the byte address. Okay, it's a basic of, so we learned the byte address in chapter 2. So actually every byte, the address 1 is assigned to the every byte in the main memory. And then what's this load word? So load word requests the 4 byte of data. So that means that this load word requests the data from address of 0000, 0001, 0002, 0003, 4 byte of data. So, and this load word requests the data to the first, the cache is checked, but this data is not found in the cache. But the size of the one cache entry is the 64 byte. So in this case, this load word just requests the 4 byte of data, but this cache requests the 64 byte of data to the low-level cache or main memory. Understand? So this load word misses in the cache request entire block of data to the low-level memory or low-level cache. So in this case, this cache requests the address from address 0000 to 0064. What's that? 0040 maybe. 0020. I don't know. So from address 0 to 63 or 63. 111111, right? Is requested to the low level memory. Okay. So address from 0 to 63. Then cache fills this data is allocated. That means that this 64-byte data is stored on a single entry of the cache, and only part of data, because this load instruction requests the 4-byte of data. Only part of data is transferred to the processor. That's how cache works. Okay. So my answer is that to Sungjun is, my answer is usually the size of a single cache entry is larger than the data unit requested by load instructions. Okay. Then before explain about the cache, I will just explain about the terminology of the cache. So when I explain about this cache, I mentioned this is the entry of the cache, but this entry of the cache is called the cache block or cache line. Okay. So usually cache block is equivalent to the cache line. Okay. So this single entry is called a block. Okay. So I frequently use the terminology line or terminology block, cache block or cache line. So you need to understand that this cache block represents a single cache entry in a cache. Okay. And then the line size or block size of cache represent the width, so size of a single entry. Okay, so in this example, I assume that the cache line or cache block size is 64 byte. So 64 byte. So that means the line size is 64 byte or block size is 64 byte. So that means the amount of 64 byte of data is stored in a single cache entry. Okay. So these are called the entry, or this is called the set. Okay. So in a direct map, the set is equivalent to the entry. So just ignore the set now, because I will explain about the set associative cache or fully associative cache later. So when we talk about some configuration of the cache, we mentioned the first, the size of cache block. So that is the size of a single cache entry. And then also we mentioned the number of entries or number of sets. Okay. So if we know the size of a single cache block and the number of entries in the cache, then we can calculate the size of cache. Okay. So if the number of entries are 8 for this cache, then the size of this cache is the 64 multiplied by 8 byte. Okay, we can calculate the size of a cache like this. So you need to remember that this, when I mention a cache block or a cache line, so that means the entry of the cache. Okay. So let's go back to the direct mapped cache. So in the previous slide, this slide shows the example of direct mapped cache, and then as you can see, this direct mapped cache includes the 8 entries. So that means, so we can use the 3 bits for the index of cache because this cache has 8 entries. And then if we see the address of this memory, so just ignore the address, byte address, just mention some word address. Okay. So if we see the address in the memory, then we can find that the lower part of the address is equivalent to the index number of the cache. And I explained that in order to identify data stored in the cache, I said we need to also store address of the stored data. Okay, but in this direct mapped cache, the lower part of the address is equivalent to the index number, which means we don't need to store this index number in the cache because it's same the index number, and then we already know the index number. Since if we just know the location of the data inside of a cache, then we know the index number. And then this index number is identical to the lower part of the address. So we don't need to store this part. Okay. But the upper part of the address should be stored. And then we need to use this upper part of the address to identify data in cache. Okay. So, which means this is the address of data. Okay. And then I said we need to store this address to identify data in the cache. But we already know that in the direct mapped cache, the lower part of the address is used as the index of the cache. And then we already know this index because the index represents some location of a target entry of the cache. So we don't need to store this part. We already know, but we don't know this part, this upper part. So cache just stores the upper part of the data, upper part of the address of data. And then this upper part of address is called tag. So it's tag. So what is the definition of a tag? What is the meaning of a tag in our real life? So we use tag like tag to identify some word or identify of some data in our real life. And it's the same to the cache. The cache stores the upper part of address as tag. And then by comparing this tag with the requested data from processor, then the cache identify the requested data is stored or not. Okay. So you need to remember only the part of their address, that's upper part of the address is stored as tag inside of cache. And then Also, initially, the cache does not have any data. That means the cache is empty. So which means a certain cache entry may be empty or may be occupied by valid block. So we need to also identify this situation. So it's empty or occupied. So in order to identify this situation, the cache has also flag bit. Okay, so the flag represents the status of a certain entry or a certain cache block. So we can use this flag bit as the valid bit. So that means that the cache entry is occupied by valid data, then this bit becomes the 1. Or if not, so that means the entry is empty. So that means the valid bit becomes the 0. So along with the data, the cache also stores the tag. Okay. So tag is used for identify data, and also cache stores the flag bits like a valid bit. Okay. So these information, valid bit and tags, is stored in the cache along with data. Okay. Okay, let's see the example. So it will be also understood. It would be better to see the example. So this is the cache example. So then in this example, the cache has 8 blocks. So which means cache has 8 entries, and then the size of a block is the 1 word. Okay. So let us assume that the word is, you can think like the word is just a 4 byte of data, but in this example, the word means the unit of the data access to the memory. So the word may be different from the 4 byte, but just understand that this is the size of data accessed by 1 memory access. Okay. So the size of the cache block is 1 word, and then it's a direct mapped cache. So in this cache, the initial state is the all entries are empty. So the valid, if we see the valid bits of the all entries of the cache, then valid bits are all zeros. Okay, and then this is the index number. Also, there is no data, and then the tags are also invalid. So this is the initial state of this direct mapped cache. And then the processor accesses this data. This is the word address, not byte address. And then in the previous slide, we assumed that the size of a single cache block is the 1 word. Okay. So this is the word address, not byte address. And then if we just represent this word address as the binary number, then that is the 01001. So that means that with the load instruction or store instruction, the processor requests this word. Okay. The processor may request the part of data from this word, but the entire cache block is requested. Okay, as I explained. Okay, so this is the word address, and then initially the cache is empty. So if we see this address, then the lower part of the address is used as the index. And then this upper part is the tag. So what does that mean? With the index number 110, we check this cache block 110, and then we check the cache, but it was invalid. So no data is in this entry. So it's miss because the requested data is not found in the cache. Okay. So this cache block is requested to the low-level cache or memory. And then if the data is transferred to this cache, then data is allocated to the which index? Index number 110. And then this is the tag. So tag is stored. So 10, and then this valid bit becomes the valid. So it's 1. So then data is stored in this cache entry. And then in the processor requests another word like word address 26, and then with the same process, this is miss because this data is not found in the cache, and then the new data is allocated to the target cache block like this. Understand? It's the same actually. And then the next turn, let us assume that the processor requests word address 22 and 26. And then this word address is the same to the word address of the previous accesses. So if the 22 is translated into the binary address, then it's the 110, and the index number is 110, and then tag is 10. So we already know that the requested data is allocated to the cache by previous request. But how can we check how can cache check the requested data exists in the cache? So this is the index. Okay, right. This is index. So with this index number, so this is the request from the processor. So this is the address. So this address has the index number 110. So we access the cache block which have index number 110, and then this index has the valid data, and then tag is the 10, and then so some data is stored. Then this is the tag. So we just compare this tag part of the requested address and the tag stored in the cache. Okay, so this is the same. But because the tag of the requested address and then tag in the stored tag are identical each other, then we can know that this cache has the requested data. Okay, because the tag is the same. The same. The data is stored here, and then this data is provided to the processor. Okay. So how can we check? The first, we access the cache entry with this index number, and then when the cache block is accessed by the index number, then we can read the stored tag in the corresponding cache block. And then if this tag is compared with the tag part of the requested address, then if the same, so it should be valid. It should be valid. The data is valid and the tag is the same. Then the data is, that means the requested data is stored in the cache, and then this data is provided to the processor. Okay. 26 is the same. Access the index number 101. Oh, it's valid. Oh, tag. Let's compare the tag. It's the same to the 11. Oh, the data is here. The data is provided to the processor. Okay. So 16 and 3 and 16. So it's miss hit. Okay. So 16 is because what was 16, the index number is the 000. So you checked here, or it was invalid, so it's empty, so it's a miss. And then the data is transferred from the low level cache or memory. And then 3, same process. And then 16, it's the same. So data is found in the cache, and this is hit. And then how about the 18? So what's the problem? The word address 18 is requested by processor. And if we translate this word address to the binary address, then this is the index number. This is tag. So with this index number, we access the cache block. But it was the 010, and then it has valid data. So we need to compare the stored tag with the tag address of this target cache block. But this is the tag of this requested data is 10, and which is different from the stored tag. So that means that this target cache block has a valid data, but this stored data is different from the requested data. Understand? Because the tag is different. So in this case, the result of cache access is miss, because the data, there is a data, but this data is not the requested data because tag is different. Understand? So this is miss, and then the existing data is evicted from the cache. It's kicked out. So, and then this cache requests data to the low level cache or memory, and then data is transferred from the low level cache or memory. Then new data is allocated to the cache, and then tag is changed to the 10, because this is tag is the tag of this data, newly allocated data. Okay, and then I explain how data is evicted from the cache. So, and then this slide shows the structure of the cache. So this is the address, and then this is the byte offset. The byte offset means that, so actually in the previous example, we just handled the word address. And then this word address is different from byte address. But we already know that in the processor, we use the byte address. But this cache has the size of the cache line is 1 word. So it's the 4 byte. So the size of the one cache block is the 4 byte. So we just ignore this byte offset part in the cache, because in a single cache block, it's 4 bytes of data is stored. So in a cache, the multiple of 4, the address of multiple of 4 is stored. So we can just ignore this part because the size of a single cache line is the 4 byte. And then this part is called the byte offset. And then if we see the number of entries in the direct mapped cache, then this example shows that, oh, there are 1024 entries in this cache. 1024 entries is the 2 to 10. So which means we can use 10 bits of low part of address as the index. But you need to note that 2 bits are used as the byte offset because the size of a single cache line is 4 byte. Understand? So this is the index part. And then among these address bit number 11 to 2 are used as the index of the cache, and then bit numbers 1 to 0 are used as the byte offset. And then remaining part is used as tag. Okay, so in this example, bit numbers from 63 to bit numbers 12 are used as tag. So this part is stored in the cache as tag. Okay. So when this cache is accessed, then we first extract the index from this requested address and then access the target cache entry with the index number. And then we can read out the tag and data and valid bit from the target cache entry. Then we can compare this tag with the tag of the requested data. Okay, so it's a comparator. And then if it's the same, then the tags are the same each other, then it becomes the 1. Also, it should be valid. So we also check the valid bit of the target cache block. So if this is 1 and this is 1, then it means the request data exists in the cache, so it's hit. Then also this data is read out by the index number of this address. Then this data is provided to the processor. Okay. Okay. So this slide also shows the example of how the addresses are assigned to the tags, indexes, or byte offsets. But this slide also shows the larger block size cache. So that means that in this example, the size of a single cache block is 4 byte. So we just use 2 bits of the LSB as the byte offset. But in this example, the byte offset is the 4 bits. So what's the size of a single cache block for this case? It's 16 byte. Okay, this is large. It's larger than the previous example. And then if the cache size is the same, then it's different. So in this example, in this cache example, the index part has the 6 bits. So how many entries are in this cache? How many entries? 2 to 6. It's 64. right? So what is the size of the cache? So this offset determines the size of a single cache block, and then this index part determines the number of blocks in the cache. So 64. So this is the 16 byte. So size of the cache is 64 multiplied by 16. It's 1 byte. So 1 kilobyte. So cache size is the 1 kilobyte, but this one cache block size is large. So what is the difference? So in the previous example, the size of cache block is 4 byte. And then in this example, the size of a cache block is 16 byte. So my question is that the cache size may be the same. Let's also assume that the cache size is 1 kilobyte. So that means that the cache size is 1024 byte. And then the first cache is the line size, is the block size of a single block is 4 byte. And then the second cache is that the size of a cache line is the 16 byte. So how many entries? So in this case, this cache has 256 entries, and then this cache, has the 64 entries. So cache size is the same. So same amount of data can be stored in the cache, but the line size is different. So that means that number of entries are also different. So why is different? Which cache is better? So think like this. How can we compare the performance of cache? So performance of cache means that the performance of a computer system can be improved by cache, but we can configure this cache as the different configurations, like the smaller line size or large line size, like 4 byte line or 16 byte of line. So we can apply the different configuration to the cache memory. So which is better? Actually, we don't know. So let's think about this small, the narrow line cache. It's a narrow line cache. So cache line size is just 4 byte. So in this cache has the large number of entries. So that means that the cache size is the same. That means the same amount of data can be stored in the cache, but the line size is small. So this cache is actually bad for spatial locality. So what does that mean? When cache miss happens, then cache requests the data which is equivalent to the size of a single cache block. So when cache miss happens, this cache, if the line size is 4 byte, then only the 4 byte of data will be requested to the low level cache. So let's think about this. The first load word requests the address 0000, and then the second load requests the address number 0004. So for this cache, this is miss first, and then as miss happens, the data is requested to the low level cache, and then new data is allocated to the cache. And then the second access is 0004, and it's possible because think about the spatial locality. The neighbor data will be requested in the near future with high probability. So what is the result of the cache? The address is 0004. It's miss because cache has only, this cache entry has only the data from address 023, not 4. So this is also miss. So the cache requests the new data to the low level cache or memory. Then how about this cache, the second cache? The line size is larger, is a 16 byte. So when the processor requests the word address 0000, then it's miss. The cache result is miss. Then cache requests the 16 byte of data to the low level cache address from 0 to 15. And then the next request is 0004. And this data can be found in this cache entry, because when the formal request is missed in the cache allocates the data from 0 to 15. Okay, so this is hit. Do you understand? So if cache has large block, then it's good for handling high spatial locality. Good for spatial locality. Okay, so it's always better. Nope. It's not always better. Is it because this cache will have larger miss penalty? So that means that when cache miss is encountered, then the cache need to request the data, and then the size of this data is equivalent to the size of a cache line. But if the cache line size is small, the cache requests the smaller amount of data to the low level cache. But if the cache line size is large, then large amount of data is requested to the low level cache. So data size is large, then it will take longer time to transfer data from the low level memory or low level cache. So miss penalty. So miss penalty means that it's the required cycles to handle miss. So if the cache line size is large, then this cache will have large miss penalty. That's the disadvantage. Okay. Also, let's focus on the number of entries. If the cache size is the same, the 1 kilobyte, this cache has large number of entries, and this cache has only 64 entries. Because this cache has more entries, then more entries may handle the more items, the more requests. But this cache has only 64 entries, so 64 large block. And then if a miss happens, then this block should be replaced. Okay, so this cache has only 64 rooms, then these rooms, so that means the entries are polluted by frequent miss request. Okay, so think like this. this is the hotel, and the hotel A has many rooms, and then but the room size is small, and the hotel B has less rooms, but room size is large. And then some customers try to book these hotels. This hotel may handle the larger people, larger customers, but this hotel just handle the smaller number of people, okay? Because there are small number of rooms. It's the same to this cache. This cache has the larger rooms, but the room size is small. And then this cache has the less rooms, but the room size are large. Okay. So it's good, but so there are advantages or disadvantages, okay, for the large block size. So and then let's see the behavioral processor for cache hit and the cache miss. So the cache hit, that means that the request data is found in the cache. So it looks like the processor access the data memory, because this is the actually data cache, and then the request data is found in this memory, this cache. So what will happen? So it will take only one cycle. For in the chapter 4, we assume that the data memory can be accessed within one cycle. So data cache also can be accessed within one cycle. So which means the data is found, then data is provided to the processor within one cycle. So the pipeline just flows as normal. Okay, just flows. But how about the cache miss? Data is not found in the cache. So and then the cache requests the data to the low-level memory. So it will take a long time. So it's like this is load instruction, and with this load instruction, we just access the data memory. But the data is not found in the data memory, then we need to wait until the request data reaches this data memory, like data cache. So load instruction is not processed in the memory stage. Okay, and then what will happen? Load instruction need to be processed in the memory stage. But if not, the load instruction cannot be propagated to the write back stage. So load instruction is in the memory, and then the next instruction is in the EX, ID, and instruction fetch stage. And then load instruction is stored in the memory stage. And then this is the pipeline processor. As this instruction is stored in the memory stage, the following instructions are also stored. Okay. The instruction fetch, ID, and execution stages on cache miss. Okay. Okay. And then there are two kinds of the cache in the pipeline. The processor is the instruction cache and data cache. If the cache miss happens in instruction cache, then we can restart the instruction fetch. So wait until the instruction data reaches the instruction cache, and then if the data arrives in the instruction cache, then instruction fetch is requested to the instruction memory. And then the data cache, I explained about this data cache. Okay. Okay, so I will stop here, and then in the next class, I will explain about how write is done to the cache, and then so different. Also, we will learn about the performance of a cache and then some different configurations such as fully associative cache or set associative cache. In the next, we learn about these different kinds of caches. And then also for the Monday class, I have some external, so I cannot have the real-time class. So that means I have some external event. So I will record the lecture video for the Monday class before the Monday, and then I will post the recorded video before the class time for the next class. Okay. Sorry about that, but I have some event. Okay. So I'll stop here. So do you have any questions? Okay, thank you for your attention. And then I post the lecture video for the next class. Okay, bye guys.